Hi there, in this video I'm going to explain partial fractions and its applications to integration. Okay, so first of all, before explaining partial fractions, I want to explain the concept of a proper fraction. So I prepared some screenshots for us to look at. So here's the first one. So here's a definition of what we mean by the term proper fraction. So a proper fraction is a fraction whereby the highest power of x in the numerator is less than the highest power of x in the denominator. So if you have an algebraic fraction, if the highest power of x in the numerator is less than the highest power of x in the denominator, then you have a proper fraction. Okay, so let's take this example. So in part A, I have the fraction 2x plus 1 over x cubed plus 2x plus 1. Okay. Now we see that the highest power of x in a numerator is 1. Okay. So the term in the numerator is 2x plus 1, and the power of x of that term is 1. And the highest power of x in the denominator is 3. So in this case we have an x cubed term where the highest power is 3, and as you can observe, the highest power of x in the numerator is indeed less than the highest power of x in the denominator. So in this case we have a proper fraction. Okay, let's have a look at another example just to make sure that we understand. So I have this example, 2x squared plus 1 over x plus 1 multiplied by x squared plus 2. Okay, now you could observe that the highest power of x in the numerator is 2, so I've highlighted that in green. And as far as the denominator is concerned, if you multiply the x plus 1 by the x squared plus 2, you're going to have a cubic term. So the cubic term is our largest term in the denominator as a result of multiplication, and as a consequence the highest power of x in the denominator will be 3, and as you can see the highest power of x in the numerator, which is 2, is less than the highest power of x in the denominator, which is 3. So once again you have a proper fraction. Okay, now you might say, why I'm explaining proper fractions? So this brings me to the next screenshot, because partial fractions mean we're expressing proper fractions of the form q of x over f of x. So q of x is a function of x, and f of x is a product of two or more functions of x as a summation of two or more fractions. Okay, so we're taking a proper fraction and we're expressing it as a summation of two or more fractions. So the method itself depends on the factors in the denominator, and I'm going to look at 3 cases. So let's go back to the paper and pen. So the first case is, so I'm going to call this case number 1. So let me take a red pen and a ruler. Now, case number 1 is the case whereby you have linear factors in the denominator. Okay, so let me go through an example to show you what a case number 1 problem looks like. So if I have a fraction of the form x plus 3 over x minus 2 into x plus 4. So this fraction that we have is a proper fraction because the highest power of x in the numerator is 1. The highest power of x in the denominator, when we multiply, is going to be 2. So in this case we have a proper fraction. So going back to this case, case number 1, linear factors in the denominator. So in this case I've got 2 linear terms, x minus 2 and x plus 4. The word linear means the highest power of x in that term is 1. Okay, So if you have linear factors, we could write this as a divided by one of the linear factors. So I'm going to take x minus 2 plus b divided by the other linear factor, which is x plus 4. Okay? So remember, partial fractions means taking a proper fraction and writing it as a summation of two or more fractions. Okay? So this is how you would write a case number 1 problem whereby you got linear factors in your denominator. Now, a and b are constants that we need to calculate. So where a and b are constants to be found. So let me show you how to calculate these constants. Okay. Now what I normally do is I call this star, so I'll call this equation star, and I always look at this this term, so the term in the denominator. So I'm looking at x minus 2, x plus 4, and I multiply this entire equation by that term. Okay, so we're going to look at 2 more cases, and I'm going to be doing the same thing, multiplying the entire equation by that term in order to work out the constants. Okay, so in my step number 1, let me multiply. So by multiplying, and I call that equation star by x minus 2 into x plus 4, so by the term which appears in your denominator here. And when I do the multiplication, I'm going to have x plus 3 on the left hand side, that is equal to a into x plus 4 plus b into x minus 2. Okay, now once you come to this step, so this step is finished, step 1 is finished, go to step number 2, and in step number 2 you need to choose a value of x to eliminate one of the terms to calculate the remaining term. Okay, so for example, if I want to calculate a, I choose a value of x to eliminate this term here in order to work out what that term a is. So looking at this term, I have x minus 2, so if I take x to be 2, as 2 minus 2 is 0, that would eliminate this term here so that I can work out the term a. Okay, so let's do that. So let's put x equals 2, and by doing this I'm going to have 2 plus 3 on the left hand side as x is 2. That is equal to a into x, which is 2, plus the 4, plus b into x, which is 2, minus the 2. So remember, we chose 2 as x because the 2 minus 2 here is 0, so that eliminates the b term. And if we simplify, 2 plus 3 is 5, that is equal to 2 plus 4 is 6, 6 times a is 6a, so when I rearrange, a is going to be 5 over 6. Okay, so remember the idea. Once you finish this step, you need to choose a value of x to get rid of one of the terms in order to work out the remaining term. So my idea is to get rid of b. So to get rid of the b term, I took x as 2, as 2 minus 2 is 0. That got rid of that b term to help me work out the a term. Okay, so in the next step, let me put a equaling 5 over 6 back into this equation here. Okay, so let me call that equation, say you can call it equation 1. So put a equals 5 over 6 into equation number 1. And by doing this, we're going to have x plus 3 on the left, that's equal to a, which is 5 over 6, into x plus 4, plus the b, into x minus 2. Okay? Now, once you reach this point, you can choose any value of x to work out b, except the value that you've used. Okay, so you can choose any value of x except the value that you've used. So we used x equals 2, and if you think about it, if you put x equals 2, that's going to get rid of that b term. Okay, so that is pointless. So you can choose any other value except x equals 2 to work out the remaining term. So in this case, if I put, so in step number 4, if I put x equals 0, say, okay, I can work out the b term. So in this case, I'm going to have x, which is 0, plus 3, that is equal to 5 over 6 into x, which is 0, plus 4, plus a b into x, which is 0, minus 2. And if we simplify this, 0 plus 3 is 3. That is equal to 5 over 6 times 4, so that is 20 over 6. Okay? And minus 2 times b is minus 2b. Okay? And if we rearrange this, you might find that the b value, or the b term, when you rearrange, is 1 over 6. Okay? So that is the constant b. B is 1 over 6, and a from the previous step is 5 over 6. So let me replace the a and the b back into equation star, okay, over here. So on the reverse, therefore, x plus 3 over x minus 2 into x plus 4 is equal to a, which is 5 over 6, into 1 over x minus 2, plus b, which is 1 over 6, into 1 over x plus 4. Okay, so let's continue in reverse. So in this case, we have x plus 3 divided by x minus 2 into x plus 4, and that is the same as a is 5 over 6 into x minus 2, plus b, which is 1 over 6, into x plus 4. Okay, so that is how you would work out the values of a and b. Okay, now why is this useful for integration? This is useful for integration because instead of integrating this horrible fraction over here on the left hand side, I can integrate these two fractions separately with one of the results that we've seen in the previous video. Okay, so let me explain. So instead of integrating this larger fraction, x plus 3 over x minus 2 x plus 4 with respect to x, so instead of integrating that, we can integrate these two terms separately. So we can integrate 5 over 6 into x minus 2 with respect to x, plus, and we can integrate the 1 over 6 into x plus 4 with respect to x. So we can integrate these two terms separately, since this term here is equivalent to the summation of these two fractions on the right. Okay? So let's integrate this. So I'm going to call this first integral star. I'm going to call the second integral double star. And let's do two side calculations, one for star and one for double star. So for star, we're integrating 5 over 6 into x minus 2 with respect to x. Okay? So what I'm going to do is let me take the 5/6 as a common factor outside the integration sign, leaving me with the 1/x minus 2 inside my integral. Now, remember one of the results that we've seen in the previous video. So here is the result. If you integrate a fraction of the form f primed x over f of x with respect to x, the result is ln the modulus of f of x plus c. So this is the very result that we're going to use to integrate 1/x minus 2. Okay, so in this case, back to the paper and pen. So f of x over here is x minus 2. So if I calculate f primed, so if I differentiate, we're going to have 1. So in this case, we're able to use this result, remember, f primed over f of x with respect to x, that is ln modulus of f of x add c. So since our numerator is the derivative of the denominator, let's apply that result straight away. So we're going to have 5/6 ln modulus of f of x, which is x minus 2, add c. Okay, so that is the result for star. Let's do the same for double star, so another side calculation. So let's integrate the 1/6 into x plus 4, okay, that we see here. So as I did with star, I'm going to take a common factor of 1/6, leaving me with 1/x plus 4 to integrate. So let's see whether this result works here also. So if I take f of x to be x plus 4, f primed, when I differentiate, is 1. Okay, so since the numerator is the derivative of the denominator, I can apply this result again in this instant here. So the result should be 1/6 ln the modulus of f of x, which is x plus 4, add c. Okay, so we have the results of our side calculations for star as well as double star. So let's use them to finish this problem. So fresh piece of paper. So in that case, the integral of x plus 3 over x minus 2 x plus 4 with respect to x is going to be, so for star, let's remind ourselves, we had 5/6 ln modulus of x minus 2, okay? So 5/6 ln modulus of x minus 2. And let's remind ourselves again, for double star over here, we had 1/6 ln modulus of x plus 4. So plus a 1/6 ln modulus of x plus 4 plus c. Okay? So that is a solution to that problem. So if you were to integrate a fraction of this form, okay, so if you were to integrate in particular a proper fraction, write it in the form of partial fractions and then integrate each of the fractions separately, okay? So, and once again, this is case number 1. So in case number 1, if you have linear factors in your denominator, you would rewrite this as a divided by one of the linear factors plus b divided by the remaining linear factor. And here is the method again in order to work out a and b. We're going to see the methods to working out a and b in the remaining two cases, case number 2 and case number 3. So I'm going to explain case number 2 in the next video, okay? And you're going to see me use the same method to working out a and b for case 2. as well as to work out the constants A, B and C for case number 3. So be sure to watch out for those videos. So that ends this video. I hope you enjoyed this video. I hope you found it useful. And if you did enjoy the video, a like is very much appreciated, and I hope to see you again. Thank you.